Chapter 5 is about the periodic table, very important part of chemistry. The book gives a little bit of the history of the periodic table. A guy named Dmitri Mendeleev was a Russian chemist, and he's generally acknowledged as the architect of the modern periodic table. He was looking for patterns and a way to organize the elements that were known at that time, and he lived back in the 1800s, so that was quite a while ago. He proposed that the properties of the chemical elements repeat at regular intervals when you arrange them in order of increasing atomic mass. So start with the light ones, the small ones, and go to the heavy ones, and what he saw was there was repeating patterns. And so he arranged the elements in what he called a periodic table because those properties repeated periodically. And he made columns looking at the formula of the element's oxides. So this is an example. Here's the general formula where R just stands for the element. And the ones in this column would all take 2 atoms of the element and combine with 1 atom of oxygen. And in this group, it was a 1-to-1 ratio. In this group, it was a 2-to-3 ratio. And so they were all different ratios of the element to oxygen. And he found patterns here. And if we look at the modern periodic table on the wall, we see that the elements here are very similar. There's hydrogen at the top, and then if we look at the second row on the periodic table on the wall, it goes lithium, beryllium. There's a gap. Then boron, carbon, nitrogen, oxygen, fluorine. And so these are the arrangements that we see in the modern table. There were some gaps. Let me go back here real quick. There were some gaps here. They say Eka, and this was, I believe, Eka boron and Eka aluminum and Eka silicon. And these were below these elements, but they were missing. They were missing because we hadn't discovered those elements yet. Nobody knew about them. But Mendeleev predicted that those elements existed and that they would be discovered. And on top of that, he predicted what the properties of those elements were. And here's a table from your book showing his predictions for what he called Eka silicon. This was later discovered to be germanium. It was discovered in 1886. He predicted its existence in 1869. You can see he predicted the color, the atomic mass, the density. The melting point was a more general, but 937 certainly qualifies as a very high melting point. The formula of the oxide, the density of the oxide, the formula of the chloride, the boiling point of the chloride. Remarkable predictions. And he did this by looking at patterns in the periodic table. What was missing on his table were the noble gases. The first noble gas was isolated from air in 1894. So when he was working on this, we didn't even know that the noble gases existed. The others were discovered in the next 5 years. The reason that they were difficult to discover is because they form very few compounds with other elements. They are inert. They were initially called the inert gases. Now we call them the noble gases because in 1962, a compound of a noble gas was made. And that was the first compound known to exist between a noble gas and another element. 3 of the noble gases, argon, neon, and helium, we have yet to create or cause to form any compounds. They just do not form compounds with other elements. When I think of, well, what do you think of when you hear the word noble? Alone? I think of the European nobility, maybe because I've been listening to a lot of English mysteries, and there's all the lords and the duchesses and stuff, right? The kings and the queens, those are the nobility. They don't mingle with the common people, right? The noble gases are like those guys. They're kind of above the rest of the elements. They're too good for the rest of us, right? And so they don't make associations with the other elements. If that helps you to remember the name of them and what they're like. The noble gases just pretty much don't make compounds. So the periodic law concept Again, Mendeleev arranged the elements according to increasing atomic mass. A guy named Moseley did some experiments and found that the nuclear charge increased by 1 for each element in the periodic table. And Mendeleev had come across a couple of discrepancies where putting them in order by atomic mass didn't quite work. And so he flipped a couple of them because it made the properties work out better. When Moseley identified the idea of nuclear charge, that fit the pattern of the properties. And so I believe there's 2 pairs of elements on the periodic table that are out of mass order. But the atomic number is the nuclear charge. The number of protons is actually the true ordering principle. For most of them, atomic mass and nuclear charge end up being the same. But for a couple of them, the order ends up being different. And so what we refer to as the periodic law is the idea that the properties of elements recur in a repeating pattern when arranged according to atomic number. So here's an example of the first, well, most of the first 20 elements. So here we go, atomic number 1, 2. Number 2 is an unreactive gas. And number 3 is a soft reactive metal. And we go 4, and there's some in here. They didn't fit in the picture very well. And then we go 9, and 10 is an unreactive gas, followed by a soft reactive metal. And then we skip another bunch here, and we see this pattern, an unreactive gas, and then the next one is a soft reactive metal. That's what the periodic law means. You line them all up, and you see these repeating patterns. A little bit like the keys on a piano keyboard, if you're familiar with that. There are octaves. There's middle C, and then you go up the keys, and they follow the same pattern, and then you hit C again. And you keep going, and you hit C again, and there's a pattern. That's what the properties of the elements do. I'm looking at this, and I know why this is here. I'm like, why is the periodic table here? Let's look and see if we can find the discrepancy. There's one, where'd it go? There's one in the 4th period, the 4th row. There's 2 elements who are out of mass order. Oops, didn't mean to do that. Here, potassium 39.10, 40, 44, 47, 50.9, 52, 54, 55, 58.93, 58.69. Nickel is actually a little smaller in mass than cobalt, but it has 1 more proton than cobalt does, and so the atomic number is the ordering property. There's another one down here, right here, tellurium and iodine. Tellurium's 127.6. Its atomic mass is larger than iodine at 126.9. But it comes first in the periodic table because it has 52 protons, and iodine has 53 protons. Okay, so we order them by atomic number. In the periodic table, we call the vertical columns groups. Sometimes we also call them families. But when we talk about a group in the periodic table, it's always a column. And there are 18 different columns or groups. And these are designated by 2 different numbering systems. Some of these groups have trivial names, other than just a number. And those are names that you need to know. And we'll look at that. We'll find those on the next slide. So vertical columns are groups. The horizontal rows are called periods. So a period is a horizontal row. There are 7 of those, and they're numbered from top to bottom. And the periodic table is also divided into some other groups. The most important ones are the representative elements and the transition elements. The representative elements are often called the main group elements. So let's look at all this on the periodic table. So here are the group numbers. The just regular numbers at the top go 1, 2, 3, 4, all the way through 18. There's been international disagreement about which set of numbers we should use. So the numbering straight across is the official recommended way. The numbers here, the Roman numbers with the letters associated with them, are an older system of numbering these groups. This is the American usage, and since we're Americans, I prefer the American numbering. And we'll see why in a little bit, but I think it's just more helpful. So this is 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. So these parts that stick up, that have the A group numbers, those are the main group or representative elements. So the representative elements, these 2 columns over here and these 6 columns over there. Those guys tend to be more predictable. And in the middle here, we have what are called the transition elements. So it looks like the periodic table, there's this valley here, and the transition elements are the transition between this hill and that hill. In the American system of numbering, these have group numbers with B's. We, personally, in the classes I teach, we rarely use these group numbers. We use the group numbers for the main group elements a lot because they help us predict charges. Down here are 2 series of elements. These are called, as a group, the inner transition elements. And there's this arrow coming down here. We really should cut the periodic table right along here and push this side over and push this side over to the left and bring this up in the middle. That makes the periodic table really long and skinny and doesn't fit on a piece of paper or a screen very well. And these guys down here are uncommon elements. We don't run into them very much. And so they just pulled them out and stuck them at the bottom, kind of like a footnote, so they wouldn't get in the way. And then the rest of these can be a little bigger. But these are called the lanthanides because they come after lanthanum. And this row is called the actinides because they come after actinium. So the names of the groups that you need to know. Group 1A, those are called the alkali metals. And group 2A is the alkaline earth metals. You need to know that. So if I say, what's the alkaline earth metal in period 3? You should be able to look at the periodic table. Here's period 3. These are the row numbers. Period 3, the alkaline earth metal is magnesium. Then over on the far right side, we have 2 named groups also. Group 7A are called the halogens, and group 8A, those are the noble gases. Now, here's a question. What is hydrogen doing floating around in the middle? Hydrogen is like the baby brother of the electron family, the element family. What happens with baby brothers? They get away with all kinds of stuff, right? You would have been taken out if you did that when you were that age, and they just get away with it. Mom laughs, ha ha ha, wasn't he cute? The truth is, your mom is old and tired, and she just doesn't care that much anymore by the time the last one comes around. So, gets away with stuff, breaks the rules. Hydrogen is like that. Hydrogen is an exception to most of the rules, okay? So in one way, hydrogen belongs over here, and that's where we see him on many periodic tables. The one on the wall here has hydrogen being in group 1A. And in some ways, he belongs there. Other periodic tables put him over here in group 7A. And there are some reasons why he belongs over there. Hydrogen is a nonmetal. The nonmetals are over here, right? So why would we put hydrogen over here? These guys are all metals. But sometimes he acts like a metal. He just can't really make up his mind. So on this particular periodic table, they've just kind of stuck him by himself in the middle. It's like, well, if that's the way you want to be, you can just be alone then. Okay? Any questions about these different parts of the periodic table? And all of this is specified and written out in your textbooks. So you can refer to that as well.